Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic, we're going to describe the introduction to approximating the solution to algebraic equations. So in this topic, we will describe what will be covered in the next few topics. Specifically, we will be looking at approximating solutions to algebraic equations. We will introduce some terminology. We will introduce the approach that will be used, and then we will describe the upcoming topics and lectures. Now to begin, in elementary school, you learned how to solve a simple linear equation. In secondary school, you then went on to learn how to solve a quadratic equation. Unfortunately, there's some very simple polynomial equations that have no exact solution. And of course, there are some equations that are just simply much more complex altogether. So to begin, a linear equation is any equation in one or more variables that can be written in the form that you were made aware of in your first year linear algebra course. Any equation, therefore, that is not linear is said to be a non-linear equation. For example, in linear algebra, you learned to solve a system of n linear equations in n unknowns, and you did this by creating an augmented matrix and then applying Gaussian elimination, now with partial pivoting, and this followed by backward substitution. You could, however, of course, have a system of nonlinear equations. And in this case, a solution to a system is any pair xy that satisfies both of these equations simultaneously. Now, given a system of equations where at least one of those equations is nonlinear, we will then describe the entire system as a system of nonlinear equations. And in general, if you have n unknowns, you will require n constraints. That is, you will require n equations. Each equation essentially provides one additional constraint on one additional variable. Now, for a nonlinear equation, the approach we're going to use is we're going to essentially rewrite the equation as a root-finding problem. So, for example, if we want to solve this particular equation, we rewrite it by moving everything to the left-hand side of the equals sign, and thus we are finding a root of the expression on the left-hand side. Any system of equations can be rewritten as a root-finding problem. So the previous system of two nonlinear equations in two unknowns can be written as follows. So notice now we have two nonlinear equations in two unknowns, and the left-hand side could be thought of as a vector-valued function of a vector variable. So consequently, we are now going to use a linear algebra approach, actually, to try to approximate these solutions. Now, apart from linear equations and systems of linear equations, we are going to reformulate all nonlinear equations to be root-finding problems, and thus we will find algorithms in order to approximate the solution to a nonlinear equation in one variable, and then proceed to approximate a solution to a system of n nonlinear equations in n variables. The first we're going to write as finding a solution to f at x is equal to 0, where f is a real valued or possibly complex valued function of a real or complex variable, respectively. The second we're going to write as a vector valued function of a vector as an argument equated to the zero vector of the corresponding dimension. X is going to be an n-dimensional vector, and f is going to be a vector valued function of that vector variable. Now we're going to assume that you know how to solve ax equals b. We will start by approximating solutions to a nonlinear equation with one variable. We're going to do this with a review of Newton's method, which you've seen in calculus, the bisection method, the bracketed secant method, and the secant method. We've already discussed partial pivoting in the Jacobi method, but we're going to extend this for approximating solutions to systems of linear equations by looking at the Gauss-Seidel method and successive over-relaxation. Finally, we will generalize Newton's method for approximating a solution to a system of n nonlinear equations in n unknowns. However, humorously enough, we're actually going to start this section with quadratic equations. So following this topic, you now have an idea as to what we will be covering in the next number of topics. You know how to describe equations as being either linear or nonlinear, and you understand that we will use different approaches for each. For linear equations, we will use the matrix vector equation approach, that is, solving a system of n nonlinear equations in n unknowns through the usual techniques. However, for nonlinear equations and systems of nonlinear equations, we will reduce it to a root finding problem. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!